more complex mission and need to do more complex parallel techniques at the same time. So I was looking into technology, conceptual technology, but with a TR level from 2 to 3 and sometimes even 4. So maybe I should have said it in the introduction. My whole research started that I wanted to find the optimized system for architectural construction on the moon. But when that started, I realized that, you know what, the space robotic itself need a lot of optimization and need a lot of development. And this is what I diverted and focused on. And I thought at the end is this robotic, or the system of this space robotics to build architecture on the moon would have to be capable of doing, whether it's the contour crafting that most of the architectural proposals include for shielding or even for the inflatable, or even to have laser or laser gun, as some people would say it. It's basically to dig and tunnel it through, whether it's the lava tubes or artificial caves, or even we create our own caves. And then we could put the inflatable or even the modular habitat inside. Now to come to the design components of it, so this is the general specs of it. If using the tires, you got 7-degree robotic arms, 4 of them. We got an extended arm over there, which I'm going to explain in the next slide. If we're going to lose the laser gun, then we're definitely going to need a lot of energy, and that cannot be produced by solar panels. And that's why I'm proposing to use a small nuclear reactor, which has been used by the Soviets in the 1950s and with the Voyagers as well. Now, the stereoscopic visions and stuff, you could tell this is almost like, let's say, pumped Curiosity rover. So I just upgraded a little bit. I didn't want to start from scratch because I want to build on what we have. So the main body is just as a placeholder. The components also are a placeholder. But then the technology developed and the ideas proposed for the components I'm going to explain next is this was what my main focus. So explaining what these extra, let's say, limb and the robotic arm would add to it is basically would give it this flexibility of not only being a rover with tires that could go forward and backward to the side, rather than this could be used as a gripping hand. Because now you got 2 tires that you could just use the distance between them. You can even help when you're going to go up in a steep terrain, which I'm going to explain in the next slide, that you could use this and give you an extra capability of locomotion on the steep terrains. Now looking at the anatomy, that looks weird. That was completely not my design. I was not even detailing anything of that. This was based on the research Arab have done in 2015, where basically they say this is the conventional structure. And we've been using this structure for the last 200 years because we've been doing things and the math by hand. We got the inertia, we got the momentum, we got the center of the gravity and the mass for the cylinders, for the plates, for the boxes, and then we combine this together and do the math. But this was 200 years ago. Nowadays, if you put this through the smart algorithm similar to this guy I've worked on, then you get optimize it more and optimize it more. So this one is 40% stronger and less in mass from the first one. And it do the exact same thing, just do it better. So the idea, this is still experimental, but we could reach to that stage. Now it's not about making it look nice, or it doesn't look nice. It does look nice, to be honest. It looks a bit futuristic. But the idea is that you would optimize the pieces of machinery we're sending to the deep space, rather than sending something that's been used for the last 50 years. So this is detailing one of the segments of the limb of the robotic arm. You can see it also goes to the inside, so it's not only in the surface. It's been optimized not on a 3D only and not in 4D in respect of time. It's been optimized in XDs, which means you could always add these properties. So what I was trying to add is, what is the lunar gravity? What are the shear forces? What are the inertia that's going to happen with these limbs if you're going to consider lifting that 1-ton weight of the robot itself? And then what are the extreme temperature we have in the moon? What are the vacuum? Because all of these things would affect the structure itself. Now, as a human, we can do a lot of calculations, but we're not that smart yet. We cannot exceed the smart algorithm that we have designed ourselves. And these algorithms could calculate all these properties, all the dimensions that you want to add, all the layering you want to add, to one equation and give you the optimum structure. So the material of the anatomy as well, that was something else I was looking at. It's why we keep using titanium. I know it's very strong and it's very efficient, it's very light, and it's very expensive. But the thing is, there are some other materials. Now over here I only explored the X aerogels, which basically mixing the aerogels with some other materials. So they mix the aerogel with the aluminum, they mix the aerogel with the titanium, and at different percentages where it reduces the thermal mass or the insulation of the aerogel, but it increases the density of it, increases the strength of it. So we could reach this new material that it's a composite that have all the materials, all the properties we need in one structure, one mold. It doesn't need to be layers anymore. And then as you can see, it already could sustain so extreme temperature, which is one of the main things that we have in the moon, especially better than Mars, that it's one of the challenges the robot will have over there. Now coming to the locomotion system, this is why I explained earlier a little bit that this is why they have the tires, the extra limb, but the idea is that you have a 3 modes. It's not only tires, it could be a quadruple walking mode, so we could walk if it starts to sink in the thin lunar regolith, and it have a climbing mode. And in the climbing mode, it's basically some of the research already trying to understand how climbers would go up. And it's not about using the same length, and you just go up putting force. Like the body, the way you climb, the chimpanzees, the chameleons, they put a lot of forces, a lot of moves. It's a lot of delicate work that if you put the smart deep learning in it, it would be able to optimize it with this lens. And this is one just to show you a scenario of, it's a failed scenario over here to the left. If you keep using your back lens to the back forward, but if you just switch them backward to the same angle of the steepness of the terrain, then it starts to help you to move forward. Now going quickly, this is the tires, and basically I was thinking of using the nanorubbles. I've been using, again, it's an example of what kind of material we can use. So I try to explore it as much as possible. But the nanorubber is basically could withstand the extreme temperature, but have a lot of elasticity. So what happens is when you use a solid tires or a solid wheels and you put it in the moon, even if you put the fence, it's gonna start to sink because the stress and the forces of the gravity of that weight of the vehicle all coming equally. But if you put the nanorubber, then the tire would basically expand when you press on it. And when you start to walk, it's going to be more surface area, which means you reduce that risk of sinking or getting stuck. This, it's a video of the chameleon. We don't have time for it. And for the dust mitigation, the last thing I looked at is basically some of the NASA people, and I think JPL, they were looking into the 3-phase dust basically repellent. And basically all of it is, you can see over here in the picture, they got the astronaut suit and they weave this nanotube carbon fibers. And what they do is, they put 3-phase electricity in it and it will repel the lunar dust. So even after they put the lunar dust on top of it, or the regolith, and then they put the energy on or the electricity on, then it starts to repel it. So I was thinking that's very smart, but what if we could combine it with our structure itself and it 3D printed it the same way that you can protect and have a void or bubble around your robot that the lunar dust will not get into your electronics. And you could do the same things with the optics for sure. Like slide for no reason, and we're done.
Good morning. Thank you very much for the presentation. It was really